So I want to illustrate how we use degrees of freedom analysis in material balance problems. So here what I've done is I've just simply shown you a block diagram, this process diagram for a mixing process where we have two inlet streams coming in and a final outlet stream coming out. And we have all the information we need about the two inlet streams. We have a flow rate here, 100 kilograms per hour, 25 kilograms per hour here. Then we have the mass fractions in this stream for components A and B. We have the mass fractions in this stream of components A and B. But we just don't know anything about the outlet streams. And what I've shown you here are all the variables that the unknown variables for this outlet stream. So we have the total flow rate, which I've just labeled here as M1. And we have the mass fraction. Mass fraction is right here. I've just labeled it as WA1 for the mass fraction of A leaving in the outlet stream, and then the mass fraction of B, I haven't identified it as an unknown variable because it's just simply 1 minus WA0. So once we know the mass fraction of A, we by default know the mass fraction of B. And so I've just written this out in terms of two unknown variables, M1 and WA0. Now, we're not going to solve this problem. We're just going to look at the degrees of freedom analysis. So the degrees of freedom is the number of unknowns minus the number of equations. And if it's 0, if the degrees of freedom is 0, then we can solve for all of those unknown variables. But if it's not 0, if it's a positive number, then we can't solve it because it's mathematically impossible. So in this case, the unknown variables, there's two unknown variables. In this case, M1 and WA0. Those are our two unknown variables. And then there are two equations. And these are two equations that come from material balance equation. And the degrees of freedom is 0, so we can solve this. And we've done problems like this many times in class and in homework and so forth. So we know how to solve this problem just by doing the material balance, writing out the total inlets 100 plus 25 is equal to M1, and then writing out a material balance for 1. Now, let me just look at a little more in detail how I got these two material balance equations. The simple rule is number of components equals number of independent material balance equations. And let me go through this in a little more detail. So I have here two components, A and B, so I can write out two independent sets of material balance equations. In reality, I can write out three different distinct equations. And let me go ahead and write those out for you. So the first set of equations I can write is the total balance. And in this case, it's just simply 100 plus 25, and of course these both have kilograms per hour, but I'm just writing this in shorthand for the example. That's the total balance. The total amount going in versus totally going out. I can write an A balance, 100 times 0.25, and again the units would be kilograms per hour, plus 25 times 0.35 equals M1 times WA0, and then a B balance, 100 times 0.75 plus 25 times 0.65 equal to M1 times 1 minus WA0. And that's the three material balance equations, one for the total balance, one for the A flows, and one for the B flows. Now you might be tempted to look at this and say, we have three different equations, therefore when we're doing our degrees of freedom analysis, we should have three. But the problem with that is that there's only two of these that are independent of each other. And that's simply because the total is equal to A plus B. So if I take this equation right here, this one for A, and I add it to this equation right here, they equal this equation right here, the total balance. And you can go ahead and do that mathematically. You can just take these equations for A and B, add them up, and it will be this exact equation right here. So what that means is that some of these, if we write out 3 equations, one of them is redundant. So let me just give you a quick example. So I have this equation over here, and this first equation is just 1/2 the second equation. So these are two equations that are not independent. They're not independent equations. So I can't use these 2 sets of equations to solve for x and y. It's mathematically impossible to solve for these because they're not independent. And the same principle applies here. We can't use all 3 equations to go ahead and solve for our variables. We can only use 2 of them. So if we think that there's 3 independent material balance equations, we would be wrong. The answer is 2. And that's simply because 2 of them add up to one of the other one. So just to put this again, to remind you, close up, that the number of independent equations, material balance equations, there may be other equations that come into play from other information besides material balance, but simply from material balances equations, the number of independent equations is equal to the number of components. So again, if I had 3 components here, A, B, and C, I would have 3 independent equations when I'm doing my degrees of freedom analysis. If I had 4 components, 4 independent equations for material balances, or from degrees of freedom material balance part. So we just need to do this degrees of freedom analysis when we have problems that are very complex and we're not sure what we need to do. It comes really in handy in helping us decide whether the problem is solvable and where we need to start when solving a problem.